Hello, everybody. Now that we've gone through the formal definition of what entropy is, let's sort of tackle entropy from a physical standpoint. Let's look at thermodynamics and see how we can get to the same result. First, let's calculate multiplicity. Multiplicity is nothing but it's just the total number of ways in which different outcomes can possibly occur. Um, so if you have more number of ways in which something can happen, the multiplicity is high. If there are less number of ways in which something can happen, the multiplicity is low. Um, to sort of drive this point home and to understand it better, let's consider the classic problem of allocating n identical objects to a set of bins, wherein we have ni objects within the ith bin. Um, Now this is a very simple problem. If you think about just the number of ways in which you can um, you know different ways in which you can place n identical objects, it is essentially the first object can be chosen n ways, the second object can be chosen in n minus one ways, the third one in n minus two ways, and so on and so forth until you reach one. So you have n factorial ways in which you can choose objects. Um, which is great. But when we're placing this into bins, we don't care about the rearrangements that occur within the bins. And therefore, let's say we had three objects in a particular bin. There are three factorial ways in which we can arrange those, three objects, but we don't care about, those six ways in which we can arrange those objects. So um, we can just divide um, 3 factorial with the number of ways. Let's say we had let's say we continue to have that same scenario, but for just one but for but the first three objects were placed like together in one bin and the rest continued, then we just have n factorial divided by 3 factorial, because everything else is just placed each bin, so to speak, just has one object. um, so the number of objects that you place in each of these bins is ni, and ni is known as the microstate. And they're known as, that's the physics terminology for it. And macrostates are is the ratio of ni over n. And to sort of really like hit this point home of multiplicity being the number of ways in which different outcomes can occur, let's look at it from a combinatorics standpoint. I hope when I said we don't care about rearrangements or other arrangements within the bin, um, everybody thought about combinatorics. We if we cared about if we cared about the arrangements, then it would be permutation. Then we just have n factorial, but we don't care about the arrangements within each of these bins. So um, let's say the first bin had one object, the second bin had two objects, the third bin had three objects, and so on and so forth. There's a number of ways in which we can allocate objects to the ith bin is essentially NC1, which is um, a very quick a very quick segue. N choose K is how we sort of look at combinatorics. We would have n objects, and you're going to choose k objects from those n objects, and the definition to sort of calculate it is n factorial over k factorial times n minus k factorial. Um, Anyway, over here, coming back to this, the number of ways in which you can, place an object in the ith bin is, for the first bin, you'd have NC1, which is you have n objects and you're going to just choose one. And then the second object, you multiply it times, you have n minus one objects remaining. So n minus one, choose two, because you're going to be choosing two objects in the second bin. And then multiply that with, now you have n minus three objects remaining, and you are going to choose three, and so on and so forth until n minus I choose I objects. And that, when you expand the terms, you get n factorial over 1 factorial into n minus 1 factorial times n minus 1 factorial over 2 factorial times n minus 3 factorial. Over here, you can see that you have n minus 1 total objects, and n minus k is n minus 1 minus 2, which is n minus 3 factorial, times n minus 3 factorial over 3 factorial multiplied by n minus 3 minus 3, which is n minus 6 factorial. This gets simplified fairly easily. You can just, within each of these terms, you can score out the denominators, and the numerator would just have, for the first one, you just have n. The second one, you'd have n minus 1 into n minus 2. And then for the third one, you have n minus 3 times n minus 4 times n minus 5. And so on and so forth, which is, um, yeah. So now this, if you look at it, this is again a series. You have a factorial as the numerator is just n factorial, and the denominator, you can see that we have the microstate factorials as the denominators, which is ni factorial, the product of the ni factorials. So that is what the multiplicity is all about. It is just the total number of different ways in which different outcomes can possibly occur. And if if human beings were great at let's say dealing with big numbers, um, we can just stop over here. But um, factorials tend to be very large and very difficult to calculate. Um, so this sets me up nicely um, for the definition of how entropy is related to multiplicity. Uh, Surprise, surprise, entropy is the logarithm of the multiplicity. Um, let's get to that. Entropy is the log of the multiplicity scaled by an appropriate constant. And over here, the constant is the number of identical objects, which is n. So you have h, which is entropy, which is equal to 1 over n times log w, w being the weight of the macrostate or the multiplicity. And that it expands to 1 over n times log of n factorial by the product of each of the microstate factorials. Now we can stop here, but why shouldn't we continue until we reach something beautiful? So yeah, let's take a deviation of Stirling's approximation. We're going to need to expand log n factorial as n log n minus n, and the way in which let me give a very brief derivation of the Stirling's approximation as well. So log n factorial is nothing but log of n into n minus 1 into n minus 2 into n minus 3 and so on and so forth until you reach 1. So you have a log of a probability, and you can log and by the sum rule, log of ab is equal to log a plus log b. And therefore, we can rewrite log n factorial as the summation of log k, where k is equal to 1 to n. And let's leave this RHS aside for now. Let's look at log x as a function and then come back to log k. Now log x as a function, I've graphed it over here. It's monotonically increasing, as you can see, and it's got well, one. Let's every point on the blue curve is log x, evaluated at that x, and the integral of log x is the area under the curve. We can approximate this integral by using Riemann sums. Riemann sums is just a fancy way of saying break up the area into to calculate the area under the curve, break up the area under the curve into equally spaced rectangles, and then calculate sum up the area of each of these rectangles, and that gives you an approximation. So yeah, if we have to find the integral of log x from 1 to n, that essentially is equal to the summation of if we had m buckets under the curve, then we would have the summation of 1 to m log of xk. This xk would be the bucket that we are at that moment, and it's typically the midpoint at that bucket, and times delta x. Delta x is the width of these buckets. And you can see that it's fairly straightforward to show that that delta x is just m over n minus 1, m being the number of discrete buckets that we have, and n minus 1 just being um, n minus 1 just being we're looking at the integral from 1 to n. So we're looking at this portion of the curve, so n minus 1. And x of k is equal to well, again we're looking at this portion of the curve. So we have x of k is equal to 1 plus k times delta x. You can see that when k is 0, x of k is equal to 1 because we're starting at 1. And if you substitute delta x for what we just saw, then x of k is just 1 plus k times m over n minus 1. Now for very large m and n, m over n minus 1 is going to tend to be equal to 1. So this term over here would just become x of k is equal to 1 plus k. That's what would happen to this term over here. And delta x would also tend to 1. So this summation over here would become log of 1 plus k essentially. And delta x is 1, as I mentioned. So you just have this integral would be log of x dx is equal to log of 1 plus k. And again, k is a large number, so we can approximate it further by excluding log of 1 plus k as log of k. And this is the RHS that we are just looking at, log of n factorial. So I've taken a deviation to just sort of show that log of n factorial is nothing but the area under the curve approximately from 1 to n of log of x dx. And yeah, this is what we were looking at. And if anyone's familiar with integration, well, this will integrate to n log n minus n. You would need to use the uh, famous integration rule of integral u v is equal to u integral v minus integral u dash um, integral v. This is and the way in which you evaluate this would be isolate. So you'd have your inverse. You need to evaluate u in the order of isolate essentially. Um, Inverse trigonometric functions, logarithm, algebraic, trigonometry, and exponential. That's the order in which you assign u of x. Over here, u of x is essentially just log x. So you can see log x dx can be written as log x times 1 into dx. So here we're considering 1 to be v. So this is just log x times integral 1 dx minus the derivation of log x times we have the integrations of both of these happening. So you have log x with this 1 dx becomes x, and log x derivation is essentially 1 over x. So you have 1 over x, and again the integration of 1 dx is x. So 1 over x times x. So x and x gets cancelled, but you still have another integral remaining. So that becomes 1 dx, that is integral 1 dx, which is yeah, you can see that over here in the beginning, as I mentioned, this log x times x, this becomes x log x. So x log x minus x. This is this is why I think anyone who if you saw this formula initially, um, well, it is very similar to the um, rule, the UV rule of integration. Log n factorial just very nicely, just becomes the integration of log x, and then that just becomes this very nice looking n log n minus n. And this is what we're going to use to sort of derive entropy. So let's do that. Let's actually derive entropy. Mm. uh, so you have h is equal to 1 over n log um, w. W is n factorial over the product of all these microstate factorials. And this can be written as, you take this up, and what do we all know about logs, which logs of a product can be written as the summation of each of these logarithms, essentially. So you can rewrite this as you can take this up, and then you can just write this as the negative uh, and the summation of log n I factorial. So you have log n factorial minus summation I log ni factorial. This we're going to apply Stirling's approximation to both of these terms, and this will become n log n minus n, and this becomes ni log ni minus ni summation I, um, and this further simplifies. Um, let's see what is happening here. Okay, for this first term, when you take n out, n would get cancelled. You just have log n minus 1. So this log n minus 1 is just this term which just got evaluated. This term over here, um, if if we expand the summation, what happens? And we also need to take 1 over n inside. So this first term will become minus 1 over n sigma ni log ni plus this ni. I mean, negative of a negative is a positive. So you would have plus 1 over n summation I ni. And this summation, I mean, the summation I and I, over here you can sort of take n inside. You take n inside, you'd have ni over n, which is essentially the probability of the ith, bin. And we all know that the summation of the probability of I is always going to be equal to 1. So this third term over here would disappear. And the second term over here, um, this term wouldn't disappear. My bad. This term would sum up, would equate to 1, because you'd have the summation equivalent to 1. You have a 1 here and you have a 1 here. So both the ones get cancelled, and you have log n minus 1 over n. Now we have we know that pi is equal to ni over n. So let's substitute um, ni as pi times the n, pi times the overall number of identical objects that we have. So that's summation I pi n times log of pi n, and this is this is quite the equation, but it's we're almost there. So you have log n minus 1 over n. We can break up this log pin into two more sums, which is the first sum. Let's take n in the first sum. We have 1 over n sigma I pin log n. This term over here, if you take n out, you see that the n gets cancelled, and we have a log n also remaining. So you can actually just take the entire n log n out. You have sigma I pi, which sums up to 1, and you have n log n, which comes out of the summation. You cancel the n, and you just have log n. So you have the first term is positive log n, the second term would equal to negative log n. So both of these terms would vanish, and this third term is minus 1 over n sigma I pi n log pi. Here you take n out, and that gets cancelled, but you continue to have the negative over here. So the entropy is the negative summation of pi log pi. And yeah, I think this negative over here is this is a negative over here, folks. um, yeah, it's a negative sign over here. And that is the entropy. Hallelujah. I hope this was um, useful, and see you next time.